Hey guys, today we're starting a new unit on work and energy. It's chapter 8, and this will bring us to the end of our study of mechanics. So today we're going to look at what is energy and what is work. So we're going to be talking about some definitions. Then we're going to look at different types of energy, and then the big kahuna, which is the concept of conservation of energy. We're actually going to get to all of that very, very quickly. And then we'll go through formulas for each one of these and run through some quick examples. Okay, so first off, we probably ought to work with the definition of what is energy, since that's what the unit is about. Well, energy is considered the ability to do useful work, which seems kind of sketchy. You think with something as important as energy that we would have a better idea of what it is and what it does than just this, just the ability to do useful work. But what we're saying is that we kind of know energy when we see it, even though we don't really know what it is. We just can tell when it's there and we can tell when it's doing something. Okay, but it gets even better because we also need a definition for work. And I'm not making this up. This is the definition of work. Work in physics is the transfer of energy. So we have this weird thing where we define these two very important terms only in relation to each other. So energy is the ability to do useful work. We kind of know it when we see it. And work, well, that's when energy is doing something. So work is the transfer of energy, and energy is the ability to do useful work. Seems odd that it would be so vague, but that's just kind of how it is, and that's the way we work with it. Okay, moving forward here. Energy is the ability to do useful work. Now, energy comes in several different forms, and we're only going to deal with two of them today. There are others, but we can understand our concepts that we need from just these two. So the first one is kinetic energy, which you have heard of before. Kinetic energy is the energy of motion, or the energy contained in a moving object. The second type of energy that we're going to deal with is potential energy, which you've also heard of. That's the energy of position. So the fact that a ball is sitting high on a shelf means that it has more potential to do work on your foot if it falls on your foot than if it was just sitting on the floor. And finally, we're going to learn about the law of conservation of energy. Which is hugely important, so much that it deserves its own slide here. Okay, the law of conservation of energy might be the most useful concept in physics. The only thing that might give it a run for its money is the conservation of momentum, which we just learned about. Anyway, what the law of conservation of energy says is that energy is never created or destroyed. It only changes form and moves from place to place. So as we go through our world and our universe, you can pause it here so you can write that down, and I'll give the explanation. So unpause it here. Okay, so we find energy in pools and in reservoirs around the universe. In stars, which are shining out energy in all directions, or lumps of coal, which we can burn and release energy, or in a cheeseburger, which we can eat and it'll give our body energy. So the energy, and the energy just moves around from place to place. And we as engineers and we as living beings just kind of grab some of the energy as it moves from one place to another. So our star, our sun, is radiating energy out in all directions. It's changing the energy from nuclear reactions and radiating it out into the universe. And as it hits the Earth and goes by the Earth, we grab some of it and we do things with it. Likewise, when water flows downhill, it's releasing energy from a calm reservoir up at the top of the mountain to a down through a river. And as it flows down the river, we can put a paddle wheel into it, or a water wheel, and make that water wheel turn as the energy goes by. We pull a little bit of energy out of that stream of energy and we do something useful with it. But the total energy of the system never changes. That's the hallmark of law of conservation of energy. The total energy of a system never changes. It just moves from place to place. And if we can make it move and predict it will move, then we can do useful things with it. But the energy never goes away, it just changes form. Okay, so we need some formulas to hang on this. The first one is for work. And as we said, work is the transfer of energy, and this is the formula that we do for work. So you need to pause this from time to time and write this all down and follow along with how we're doing this. So W stands for work. The units of work are in joules, and we'll get to that in just a second. F is force, and D is distance. So the way we define work in physics as applying force through some distance. So let me go to the camera here and show you what I mean. Okay, so I have a bowling ball here, and I'm applying a force to this bowling ball to keep it from falling to the floor. But according to physics, I'm not doing any work on this ball because it's not going anywhere. To make it go somewhere, I have to push it through some distance. So I am applying force to the ball, and when I move it upward, now it's going through a distance, and that means that I'm doing work on it. Likewise, if I take a stool, there's friction against the floor. So I have to apply a force to it to make it move across the floor. Now, when I'm just leaning against it, it's not going anywhere. I'm not doing any work because there's no distance. The distance is zero. But if I apply the force and it moves through a distance, now I'm doing work. All right? Let's go back to our slide here. There we are. Okay. So the units of force are newtons, kilogram meters per second. The units of distance are meters. We multiply them together and we get this weird unit, kilogram meters squared per second squared. And that really is a mouthful, and that's why we call them joules. That's spelled Joules, joules. It's named after one of the physicists in the 1800s who worked a lot of this out. So kilogram meters per second squared, that's newtons. We multiply that by meters. We get meters times meters is meters squared. And everything else stays the same. Okay, we call that a joule, as we said. Let's see. Yeah, okay, that's what I just had down here, so we'll leave that. Okay, now let's do a little bit of work. I will go back to the camera. As you know, this bowling ball has a mass of 7 kilograms. So the weight of the ball is 70 newtons. 70 newtons. 7 kilograms times 10 meters per second squared is the acceleration due to gravity. So the weight of the ball is 70 newtons. And that means that I have to apply 70 newtons of force to this thing to keep it from falling on the ground. Now, once I get the thing moving and start accelerated upward and keep it moving, I still only have to apply 70 newtons to keep it moving at constant velocity upward. Okay, so sitting on the ground, the height is 0. I pick it up and I apply 70 newtons of force to it through 2 meters. That's about how tall I am. So I have just applied 70 newtons of force through 2 meters of distance. And we're going to figure out how much work that was. So here we go. Work is force times distance. I did 70 newtons of force times 2 meters of distance, which means I did 140 joules of work on the bowling ball to lift it up. Okay, remember that number, 140 joules, and you should be able to do that math. 70 newtons times 2 meters. Okay, now we're going to look at the formula for potential energy. So potential energy is the energy of position, meaning that something that is sitting higher has more potential energy than something sitting lower. It has the potential to do work on my foot if I drop my bowling ball on my foot. And the formula is PE, potential energy, is equal mgh. M is mass in kilograms. G is the acceleration due to gravity, 10 meters per second squared for us. And H is the height in meters that the thing is lifted against some reference height. And when we put all that together, kilograms, meters, meters over second squared, we get joules again. So the units of potential energy are joules, just like the units of work were joules. Now let's figure out how much potential energy my bowling ball has. when I lifted it up, as I just showed you before. So I lifted the 7-kilogram bowling ball, so it was 2 meters off the floor. 7 kilograms, 2 meters high. We got to multiply it by 10 because that's G, and we wind up with 140 joules again. So what we see is that I am doing work on the bowling ball. Right now, the bowling ball has no potential energy at all. I do 140 joules of work to lift it, to lift it over my head. And once it's up here, now its potential energy is 140 joules. So the work I did is equal to the energy that it now has. That's not a coincidence. Next, we're going to look at kinetic energy. Here we go. Kinetic energy. As you remember, kinetic energy is the energy of motion. So it's the energy that a moving object has because it is moving. And the formula for it is 1/2 times m times v squared, where m is the mass in kilograms and v is the velocity in meters per second. And we have to square that. So that's why I have meters per second, quantity squared. All right. Now, when we multiply all that out, we wind up with kilograms times meters squared over seconds squared. We get joules again. So our formula for kinetic energy spits out joules, right? So you might want to pause this to write all that down because this is an important equation that you have to know, and you have to know how to plug stuff into it. And we're going to do that right now. Okay. Suppose I drop my bowling ball. I have it up over my head, 2 meters off the floor, and I drop the ball. Now it's going to go faster and faster as it comes down to the ground. First question we have is, well, how fast is it going when it hits the ground? And the answer is 6.32 meters per second. You guys are capable of figuring that out. And if you want to go through that for practice, you can. Yeah, basically you figure out the 2 meters, figure out how much time it's going to take to fall to the ground using d equals 1/2 at squared. And when you have the time, then you use v equals at. The final velocity is the acceleration due to gravity times the amount of time that it falls. When you do all that, you get 6.32 meters per second. Now, what I want you guys to do for sure is to plug this value into this equation and figure out how much energy, how many joules of energy the ball has as it hits the ground. Okay, so you're going to use the mass of the bowling ball, which is 7 kilograms, and the velocity of the bowling ball when it hits the ground. And remember, you have to square it. Okay, so you do that math. Hopefully you won't be too surprised by the answer. And the answer is, drum roll, 140 joules. 140 joules. So the work that I did, this is to summarize it here. The work that I did to lift it off the ground was 140 joules of work. When it got up here, it had 140 joules of potential energy because I transferred 140 joules of energy from my body, from the oatmeal that I had for breakfast this morning, through my mighty musculature to lift the ball. I transferred 140 joules of energy to it by lifting it and raising it above my head. So now it has 140 joules of potential energy. If I now drop it, it's going to fall. And as it falls, it's going to be going really fast when it gets to the ground. And it will have 140 joules of kinetic energy when it lands on my foot. And that 140 joules of potential energy is capable of doing work on the bones in my foot and breaking my foot. That's why I don't drop it on my foot. Okay, so what we've seen here, this summarizes it. You might want to pause it all. What we've seen is that joules is joules. The joules that appear out of all of these different formulas, the work equation, potential energy equation, kinetic energy equation, it all comes out to joules, and all joules are the same. So we actually call this idea the work energy theorem, the idea that the mechanical energy in a system is equal to the work done on the system. Again, the total amount of energy, once I do the work to transfer the energy from my body to the ball, then it doesn't matter where it is or what it's doing, the energy of the ball stays the same. until the ball hits the ground and transfers its energy to the floor. And then the energy escapes from the ball and goes somewhere else.